Okay, so welcome everyone to this, I believe, sixth lecture. And let's start with some questions. I'm going to go over some of the stuff from last time. So if you have questions about entropy, maybe you should hold those. But do you have any more other questions? So,
sorry, did you resolve that thing that we were talking about at the end of the class with the irreversible process?
Yes, I did. Yes. I'm going to go into that today. Yeah. It's actually quite trivial. Yeah. It's a very subtle subject. It's not very complicated mathematically, but conceptually it is subtle. And we're going to do some examples today so that some of the subtleties can be fleshed out. Like what does it mean to have an irreversible process? What does it mean to have the entropy of an irreversible process? And how do we actually measure the entropy of an irreversible process? Okay, so we are going to do some examples today, which hopefully will clarify those things, okay? All right, so let me just do one more thing. It's very hot in here, so let me turn on the air conditioning before I start. All right. Any other questions?
Sir, I had a question.
Yeah.
Is it all, I mean, for any 2 points in the state space, is it always possible to find a path that is reversible?
Not really, no. I don't think so. I think it depends on the system and what you Mike, I don't think so. I don't think there has to be necessarily something very well defined. There could be, and we always have to look for it. So there could be, we could have problems computing the entropy, right? So yeah, that's a very good question. I don't think the answer is yes to that. But it's let me also come back to that because I do. Yeah, that would be my answer. That doesn't have to be, but in many cases, most of the cases we're dealing with, there is. Okay.
Okay, sir.
All right. Any other questions?
That actually reminds me that I think there was a participation quiz question that was related to that, like true, false, or which of these statements are true. One of the statements was this one. I actually got that one wrong.
So what was the statement?
I'll have to check it. Let me go on Buxton's.
I don't think it was explicitly that statement.
Yeah, I don't think it was that statement. But anyway, it may have been. So, okay, Saib, why don't you message me about that? And then I can look at it afterwards, okay?
Yeah, sure.
Okay,
yeah,
so
I saw it wrong too.
Did Afia come in? I thought I saw Afia come in. So, Afia, are you there?
Yes, sir, I'm here. Sorry.
All right, no worries. So we are missing Nusaiba, Mehdat, Zakaria, and Oishik. And Mahfuz, of course, doesn't have good internet connection, so he can't. So if you guys, any of you, look, the reason why this class has like a quote unquote mandatory attendance policy is because I feel that most of you do have good internet access and that you are able to, you should be able to join this class. The more students are joined in the class, the better the class goes and the better your education is. But if you do have a technical problem or you have some other obstacle in being able to join the class online, please let me know. I will relax that condition for you, okay? So for example, if you're in a place in Bangladesh where, the internet connection is not good, or you have some financial problem where you don't even have to tell me exactly, what it is. You can just reach out to me privately, and I will make sure that either you're supported or that I relax the condition. Okay, so this is just the mandatory attendance policy is actually to encourage, is not for me to impose my power on you. That's not really what it is. I don't care about those kind of stuff. It's just to make sure that people are engaged in the class. Okay. All right. So let's start, and let us start by reviewing entropy. Okay. Let's review entropy, and we'll have much to say about entropy in this course. So entropy is a function of state, right? So S is a function of state. That means that it only depends on the state variables at its equilibrium value. So for the ideal gas, it's going to be a function of P and V. And it doesn't matter how one got there. The process can be reversible or irreversible. It just so that's basically what a function of state is. It only depends on the value of the state variables. So of course, we got clued into the fact that there is such a state variable by considering reversible processes. So what we did is that we took a reversible process, a system with a reversible process, and we computed this combination of quantity on a closed loop in the state space, and we found that this was 0, and that's really means that if we have 2 points, so if the path that we took in state space was between 2 different points, say SA and A and B, then the difference in entropy is given by this. So usually when we define the entropy of a state, we define it with respect to some reference or fiducial state, and let's call the reference state 0 or O or whatever. So S of A is defined to be, we think that there is a reversible path, D of S, D. Now, as Nian was asking, whether such a path exists or not, it may be that this path is very hard to find. Okay. Muhammad Abdullah is here, so let me make sure I give you your, oh yeah, you were already there. Okay. So people are like zoning in and out, I guess. The internet is not very stable. All right, so the infinitesimal version of this equation is that the infinitesimal delta S is given by, del d of Q reversible divided by T. Okay, so this is the infinitesimal change of entropy. So now let's talk about entropy of an irreversible process. So because that's where entropy becomes interesting, but it's always interesting. But okay. So suppose we have a system which undergoes a process from, say, state A to B. So the system takes the path 1, which is from A to B. Now, for the moment, let's assume this path 1 is irreversible. So, for example, it could be, where there's friction involved, so that we can't go back, or we can well, let's postpone the specific discussion of specific examples a little bit later. And suppose that there's also another path called path 2, connecting those same 2 points, A to B, which is a reversible path. Now, we saw that there was this inequality by Clausius, and what Clausius's inequality says is that for any general path, so this is not necessarily reversible, for any general path, this is less than or equal to 0. And let me just remind you that if this path was reversible, if every aspect of this path was reversible, then Clausius's inequality would be saturated, because that's exactly how we defined entropy in the first place. We derived something like this, and then from there we deduced that there exists a function of state. Okay. So now let's draw some pictures, and again, this is all review from last time, but I think this is conceptually subtle. So this is some state space. So this could be P and this V, and this could be P, and we have some point A and B, and so this is path 1, which is irreversible at the moment, and this is, say, path 2, which is reversible. And then from Clausius's statement, what we can do is that we can write this out as the integral over along path 1, which is dq over t, that is less than or equal to the integral over path 2 dq reversible over t. But the right-hand side is S of B minus S of A, right? So what we found is that, well, I'm just going to write S of B minus S of A is greater than or equal to the integral over path 1 of dq by t. Okay? So now let's put on some restrictions on the systems. So let's say that our system was isolated when it moved through path 1. So it was moving to path 1, and the change was adiabatic. Isolated meaning adiabatic. There was no heat coming in or going in. That meant that this was always 0 for that path. And that means that the change in entropy is greater or equal to 0. Okay, so remember that. So in irreversible path, irreversible adiabatic path, the change of entropy is greater than or equal to 0. Okay, so this is the infinitesimal version of this equation. So this is for irreversible and adiabatic. Okay, so by isolated, I use the word isolated here because if you isolate the system, of course, it is going to be adiabatic. So what this is saying is that for isolated systems, the change of entropy with time is either 0 or greater than 0. Okay. Now, if the path was not just adiabatic, but reversible, if one was, adiabatic and reversible, then, this thing would be, this thing would be saturated. The Clausius inequality would be saturated. And then in that case, so in that case, we have basically S of A would be equal to S of B. So it's only for isolated and reversible, processes that the entropy is going to be unchanged. Okay.
So what is the meaning of saturated?
Sorry, can you be a bit louder?
So what is the meaning of saturated?
Oh, saturated means that when we have, so this is Clausius's identity. Whenever we have an inequality, and the inequality tells us that, the left-hand side, so if this is the number line, and so this is the number line, and this is 0, and this inequality means that the left-hand side has to be on the left of the 0. So when I say saturated, it means that it is going to be exactly at 0. It is at the boundary of this inequality. That is basically what saturating an inequality means. Okay.